Welcome to the 4th academic seminar. In order to get those PEP hours, make sure to fill out the feedback form by this Friday and fill out the sign-up form if you haven't already. There are also YouTube recordings of the academic seminars 2 to 4 and industry talks 2 to 4. So if you've missed any, watch the YouTube recordings and fill out the YouTube attendance form to get those hours. For more info about the PEP hours, please check out the SUCE Facebook page. It would be appreciated if you could turn on your cameras as well to make David feel more welcome. Today we'll be joined by Professor David Airey, who will be giving a presentation on soil mechanics and ships. Professor David Airey grew up in the UK in Cornwall and undertook his education in the University of Cambridge, including a Bachelor in Engineering and a Master's and PhD in soil mechanics. He then pursued a position as a research fellow in the University of Western Australia for 2 years. In 1989, he started teaching at the University of Sydney and has continued teaching here for over 30 years. His main interests of research are in soil behavior and experimental geomechanics. Outside of this, he is a keen surfer and sailor, currently sailing a laser at Double Bay Sailing Club. So I'll pass it over to you, David.
Okay, so hopefully you're seeing my screen now, all right?
Yep, we can see.
Okay, so welcome everyone. So I didn't know quite what to expect. I had a brief chat with Victor, who suggested I could talk something about the research that I do. And we had a brief discussion about topics of which I had suggested a few, and we ended up with soil mechanics and ships, because soil mechanics and ships don't go together. Okay, so for those of you who haven't done soil mechanics yet, you don't appreciate this, but I'll come to that in a minute. Okay, so basically what I'm going to do is, and I'm not going to talk too much about soil mechanics, okay, because we don't want to get stuck in the technical details. So I'm going to spend a bit of time explaining what the problem is, and then say, what's been done and what we did here at Sydney University, very, very briefly. Okay, so there's a few graphs, but we're not going to go into any technical details. So let's get started. So firstly, I was told that most of the audience would be first and second years who hadn't done soil mechanics, but I noticed there's a few names I could see that actually have done soil mechanics. So just bear with me for this first bit. So this is really directed at those of you who haven't yet taken soil mechanics. Okay, so what we're normally concerned with in soil mechanics is whether buildings, buildings sit on the ground or we have tunnels in the ground, and we want to know whether they're going to stand up and be stable. That's traditionally that was one of the big issues. The ground is definitely the weakest bit of the whole civil construction process. And then if we get a bit more sophisticated, we want to know how much the ground moves. So if you put a building on the ground, if different bits of it move by different amounts, that creates distress in the structure. And so we need to be able to understand and control that. And then there's a whole lot of other issues to do with the interaction of the soil, of weak, soft material with the structure, very stiff and strong, that sort of form the basis of geotechnical engineering. So that's kind of what soil mechanics is about, and the course, when you do it, is concerned with those issues. Now we need to understand, what we're talking about with soil. So the main issue is really the material. So we need to be aware that we're dealing with a natural material. So soil, it's come from rocks that are broken down generally, and we have particles that vary in size very significantly, and we have a variety of minerals. So that creates a whole lot of uncertainty, and because it's a natural material, it's incredibly variable. Okay, so we're always dealing with uncertainty, and there's lots of stuff we don't understand or know very well about the ground behavior. Then the other issue, which is sort of critical and why it is that we end up studying soil mechanics, is all to do with the space between the particles. So that space is filled up with something, and the something is usually water. But in the case of the ship issue, it's a combination of air and water, and that is what creates a lot of the issues that I will later come on to mention. So the other thing we need to be aware of is, what are the important aspects of the soil material? So I'm assuming you've all done a little bit of civil engineering now. So you're used to sort of steel, concrete, these are stiff, strong materials that have a strength. So when we're dealing with soil, it's made of particles. The only thing that gives us strength is friction. So the friction between individual particles, and that depends to some extent on the size of the particles, and the size is tied up to the mineralogy. So we have a range, a factor of about 2, from clays, which are the weakest, to the larger, harder particles, gravel size, which are have maybe double the frictional resistance. So that's one issue. And then the next thing, and by far more important, is the ease with which water can flow through the soil. So here we're not talking about a factor of 2. Here we're talking 10 to 15 orders of magnitude difference between the clay used for to contain a radioactive waste to gravel. Okay, so 15 orders of magnitude, an enormous range of values, and that has a big influence on soil behavior. Okay, and the other aspect about soil which makes it both interesting and challenging is the fact that it has significant volume changes when you load it. Okay, so we won't get into all of those things now, but this is just to give you a bit of a feel for the sort of issues that we're involved in. Okay, so that's my brief intro to soil mechanics. So now let's have a think about the background to the issue with the ships. Okay, so basically ships have increased in size enormously in my lifetime. Okay, so prior to the 1960s, ships were pretty small relative to what you see today. Most of the bulk carriers, which is what we're concerned about here, were just coastal, generally going short distances, usually could manage to not go out into a storm in the first place because they were only just hopping along the coast somewhere. But nevertheless, small ships are actually the worst for getting rocked around in the sea. And a lot of ships were lost, right? And if you think about over history, there's shipwrecks everywhere. So there was an issue, and there was an increasing concern with the number of ships carrying bulk products, so mostly coal at the time, that were sinking for unexplained reasons. And that led in 1960 to what was a first, right, which is SOLAS, which was a conference which was Safety of Life at Sea is what it stands for. Okay, so that 1960 was the first time anyone really worried about it, which is extraordinary, right? And it led to what's called the Proctor Fargerberg test being introduced in 1965, which is still what we're using today for looking at whether a cargo can be safely transported. It was initially just advisory, but since about 2008 or so, it's become mandatory. Okay, and that's kind of part of the issue why I'm speaking to you about this today. Okay, so that was in the 1960s. Since then, boats have got a lot bigger. In the 1980s, there were some issues with coal. A number of ships carrying coal sunk. And you need to understand that the 1980s was not a good time economically. Basically, all these boats, they didn't have much cargo. They were rusting and going nowhere. So there was a lot of suspicion about why these boats were sinking and the insurance being claimed. And it turned out that most of them sunk not because of problems with the cargo, but because the ships were no good, or the owners were happy for them to be sunk. Okay, so that was, and then basically since the 1980s, there was no interest in cargo in ships. People were using the testing, and I'll come to why things changed more recently. But just so we're aware, bulk carriers have a bad safety record. Okay, shipping's a dangerous thing. So you can see the numbers there. A lot of ships, and these are not little ships, right? These are big ships that have been lost at sea, and a lot of crew lives have been lost. So it's 100 ships out of a total of about 6,000 or so. But these are big ships. They're worth millions of dollars, and a lot of the time it's due to the structural issues. Okay, or maybe navigation, they run aground and break up, but also just the structure of the ship, badly designed or whatever, fatigue type failures, and the steel problems that occur. But what we're concerned about is when the cargo shifts and causes the ship to sink. So this is referred to as a liquefaction type failure. Basically, the cargo loses its strength, and what happens then is that the ship can very rapidly list and capsize and sink. And because it's a rapid failure, that's why there's such a large loss of life. Okay, so we've actually got no evidence that this happens. Okay, you need to understand this is no actual evidence. It's basically a supposition. Largely a supposition from the fact that the ships sink quickly with no warning. And it's inferred that it's a cargo shifting issue. So we're primarily looking at cargoes of iron ore, nickel laterite, which is basically iron ore, bauxite, and coal. They're the cargoes that are of the most concern. And just to give you an idea, I've got a picture there of the Stella Daisy. Okay, the Stella Daisy is now at the bottom of the Atlantic Ocean, somewhere in the halfway between South America and Africa. Okay, so it was carrying 250,000 tons of iron ore. So you know the price of iron ore, if you've been paying any attention, price of iron ore is sky high at the moment, $200+ a ton. So there's a lot of people concerned when a ship like this sinks. They're all insured. Someone has to pay up. There's a lot of money involved. I mean, the ship costs a lot of money. There's a lot of money in the cargo, and the crew only one person on the crew survived the sinking of the Stella Daisy. Now, it turns out that people don't believe it was a liquefaction problem. They believe that it was a structural issue, but it will never be proved because the ship is in 4,000 meters of water or something. So we'll never really know the answer. Okay, so why did I get involved in this? What happened was in 2011-12, there were three fairly large bulk carriers. They were about 50,000 tons of iron ore, that sort of size, sank in quick succession. They were actually almost, I think they were all going from India to China. But the consequence was that the authority that looks after this, the International Maritime Organization, reclassified iron ore as a Class A cargo. Now, the consequence of being a Class A cargo is that you have to check the moisture content. You have to do this Proctor Fargerberg test to make sure that the cargo is safe to ship. And the three main companies, so if you look down at the bottom, you'll see Australia and Brazil are the two main iron ore. Australia, the 44% from Australia at that time was just from two companies, Rio Tinto and BHP, and the Brazil bit is all from one company, that's Vale. Okay, so there's three big players here, and they're all suddenly being told that they've got to do this test. They've never done any research to find out about what this means, and they're all extremely worried. They all have an industry that's, each of these companies has a $6 billion industry that's making over 100% of their profit in at least two of those companies' cases. and it's potentially going to be shut down because they don't know what's going on. So there was a lot of interest in trying to understand what the TML meant, okay? Because this was something they'd never done, and it potentially had the ability to stop their shipping, and they were also concerned that their competitors might get an edge on them. So this is where I came in. I mean, it wasn't just me. There were a lot of people all around the world who were engaged by the various iron ore companies and by the International Maritime Authority to look into the problem. Okay, so just so we understand what's going on a little bit. Okay, so I've got a picture there of iron ore finds at the port. Okay, so you mine this out as a rock. It gets milled up at the mine site, which involves water. It then goes into a train, comes to the port, put in the stockpile. You can see they're spraying water on it to keep the dust down, okay, so, which is a big issue with iron ore in particular. And then it gets shipped into the, along a conveyor belt into the ship. Now this picture in the middle is basically a robotic laboratory where they check the quality of the iron ore finds. So as it goes along the conveyor, they, at regular intervals, take samples and they check the grading, the size of the particles, and they check the water content. And this is all done by robots. Okay, there's no humans involved. And then it gets loaded into the ship. You can see the process there. It varies a little bit from place to place, but the three big players, it's all essentially looks something like that. Okay, so that's what we're dealing with. And when it gets put into the ship, we're on picture, looks like on the top right here. And on the top left, on the top right, we have what happens when the cargo becomes liquefied. Okay, so you can see that it shrinks apparently, and we now have water sitting on the surface. So how does that process happen is sort of, one of the challenges to understand that we've been looking into and trying to be able to predict exactly how that process happens. And this is actually a very difficult soil mechanics problem. Bottom picture is a ship where the cargo did, and this is one that's well documented where this happened, the cargo became liquid, it shifted, and this ship, the Trans Summer, capsized, as you can see, yeah, so that's what we're trying to avoid. Okay, now, I'm going to try to explain the soil mechanics of the process, okay? So I've just taken this from the Australian Maritime Safety Organisation, that's AMSA's website. So there's a debate about the mechanism, okay? So traditionally, people have said it's liquefaction, and then there's been some recent research, which is a consequence of all these issues, and they've now come up with this term dynamic separation. So first picture, okay, is the same in both columns, both of the situations. This is when you load the ore onto the ship. Okay, so the iron colored bits, they're the ore, and then in between the ore you have the space, and the space is filled with blue stuff, which is water, and white stuff, which is air. Okay, so this is important. The air in here is important. Now, if you're shipping, okay, the last thing you really want to be doing is transporting water, because if you're filling up your ship with water, then you can put less iron ore in it, and at the other end they don't want to receive water, they want to receive iron ore. Okay, so we're going to be concerned at the other end when there's lots of water, but generally there isn't much water. Okay, there's lots of air. However, the problem only occurs when we have lots of water. So we start off with this soil in a fairly what's called a loose state. Okay, so those of you who haven't done soil mechanics before, basically when we're looking at the ground, we normally want to make it dense as we can make it for deformations to be small. But when that process that you saw of how it's loaded into the ship, we end up with very loose material. So when it's loose, this is when you can get liquefaction. Okay, so if we come to the bottom picture, this is meant to be their liquefaction. Okay, and some of you may be familiar with this from the issues I had in Christchurch. Okay, so what happens is you have a very loose soil, it gets shaken, and the soil wants to settle and compress. The water, however, is very stiff. So it transfers the load onto the water pressures build up, and the soil loses its strength. Now we've got large water pressures, and that causes the soil and the water to then flow up to the surface. However, when you're looking at the liquefaction problem here, we don't get to the flow problem. Basically what they're saying is we get the water pressures building up, we lose strength, and when we've lost the strength, then the cargo is free to just slop around and the ship can list and fall over. With the dynamic separation, this is more like what actually happens in liquefaction problems due to earthquakes. So the soil settles, that causes the water pressures to build up. The finer particles then flow up to the surface with the water, and you have water now sitting on the surface of the cargo. And simply the action of this water and the fine material that's in it is sort of a heavy fluid. The fact that that just slops from side to side is enough to cause the ship to list. Okay, and then ultimately, if that happens too much, failure. Okay, so we've gone fairly slowly for now, so I need to kind of speed up a bit. But so here's the Proctor Fargerberg test. Okay, so this is how you decide whether the cargo is safe to go. So those of you who've done soil mechanics will be familiar with this. This is just a standard compaction test where you take the soil, you mix it up with a bit of water, and you have a little hammer, and you squash it into this cylinder, and you produce a graph here. Okay, so void ratio, it's how much space there is relative to how much solid, and plotted against the moisture content. And the magic moisture content is when you get a degree of saturation of 70%. So anything less water than that is safe, and anything over that, potentially a problem. So the idea is this curve is not unique, okay? So this is the problem. The curve depends on the density that is produced by the shipping. And this is one of the issues with this process. You have to know what size hammer to use to represent the situation in the ship. So it's not a very rigorous procedure, but this is the procedure which is used. Okay, so just so we can understand why research is being done, the TML was introduced. The iron ore producers were very worried about this. They wanted the value to be as high as possible because they were concerned that they would come and load up their ships and then find that they couldn't, they weren't allowed to. And indeed, this actually has happened in Australia. And when that happens, they have to actually dig it out of the ship, which is actually a big issue for them because the ports are not designed for digging cargo out of the ship. They're designed for filling them up. So when that happens, it takes them about a week to empty the hold. All the ships are backing up. And as you've heard with the evergreen thing in the Suez Canal, when the ships start backing up, the costs of the delays to all the other ships start to very rapidly add up to tens, millions, hundreds of millions of dollars. Okay, so this is a big issue for the shippers. Of course, if you're an owner of a ship, the insurer or the crew, you're very interested in the TML because you want to get to the other end safely. The test itself, as you've seen, it's a very simple test, but how uniform is your product? How often do you do tests? Whether it depends on the user. Okay, so, you know, those of you who've done the compaction test will be aware that it's not a very, you know, rigorous sort of test. So there is an issue about repeatability of results and so on. Okay, and then we've got to remember that we're doing this test all around the world. It needs to be quick and simple, and it needs to be conducted at remote locations where equipment and so on is difficult to come by. Okay, so from the soil mechanics point of view, we know that the loading ends up with a very loose soil. And if we have very loose soil and we start shaking it, we know that liquefaction occurs. So we're immediately in a situation which is potentially a problem. But the thing is, the soil is not saturated, okay? As I've explained, you don't want to have water in it, but there is always some water due to the processes of the mining and the dust suppression and so on. So when you put the ore into the ship, there's a process of consolidation and moisture redistribution that takes place, okay? And there's some flow of the water. So, okay, this is something we talk about in soil mechanics. It's a little bit more tricky here because the soil is not fully saturated, but the process is essentially the same. Those who've done soil mechanics will understand. Then there's an issue about the mechanical behavior of iron ore fines or these other products which are shipped. It's a granular product, but is it the same as the soil that we're familiar with it? And the reason that's an issue is because the models that we have are almost entirely empirical. Okay, they're just based on experience, and then we produce some very fancy models which reproduce the behavior. So if you have a new material, is it going to behave the same is an issue. And then we're applying cyclic loading, which is a problem to get good results predictions. And then it's also unsaturated, which is again another issue where we don't really have a good understanding of the behavior, particularly joining saturated and cyclic together. So there's a whole lot of uncertainties in the soil mechanics. And does the TML, this simple moisture content test, does it capture all of that? And can we say that it's safe? Okay, so this is really the fundamental research question that we're trying to answer. Okay, so what did we know? We knew there's work done in the 1980s on coal. Interestingly, I was sharing the apparatus with someone who did a lot of the key work when I was doing my PhD. There were some tests done again back in the 80s with centrifuge. I'll show you a picture of centrifuge in a minute. This is a modeling procedure, and basically it suggested that water flowed to the base and then it could liquefy. But that really hasn't flown on into any change to the shipping process. Another issue that we faced when we started looking into this problem was that we had no data. Okay, there's no data on what was happening in the hold of the ship. And partly because the iron ore companies said, well, we have no issues, so why should we take any measurements? But also, when confronted with a problem, we said, well, the normal thing is to take measurements. And we were told, no, there is no way you can take measurements. So one of the issues was we couldn't put any instruments into the ore because there was a big penalty on the shipping company if there was things that shouldn't be there when it arrived at the other end. Okay, so they weren't keen to put anything into the ore for that reason. There was also concerns about safety. So despite having an industry worth $6 billion and being told that it might have to stop, safety trumped any concern there, and we weren't allowed to get into the hold. And another issue which is important, because as I'll come to very briefly at the end, is drainage is an important issue, and ships have bilges at the bottom which are meant to let the water drain. But whether they worked or not, and whether the ships even tried to make them work was unclear. Okay, there was a belief that the size of bilges were still the same as when ships were 1/10 the size that they are today. They're not sufficient, and then they cover them up because when you get the iron ore into the bilges, it's a real mess. So basically, although they have a bilge, which would definitely help their problem, they're not effective in practice. And there was a lot of work was done at the same time as we were doing our tests to look into these problems by, this is the technical working group of the IMO and bauxite working group, okay, which were really the mining companies basically looking after their own interests. They sponsored this research so that they could work out how they could safely ship their product. Oh, sorry, that's, we've gone on way too far there. I was pushing end. Sorry, got to go back. Sorry, I'm going to have to. Okay, so I'm going to go fairly quickly now through what we've actually done, because this is where it gets a bit technical. Okay, so I was employed by Rio Tinto. We did a lot of work looking at TML. We actually dropped ore 10 meters off the side of the electrical engineering building to look at what happens when you load it into the ship. We did a whole lot of triaxial tests, but I can't talk about the results because that's all confidential. But what happened at the end of that is we went on to do some further study funded by the government to try to look at more fundamentally the soil mechanics issues. So it's not about whether iron ore can be shipped safely, but you know, if the product changes over time, what are the key issues that, or key factors in terms of the material that influence whether we've got a problem? Okay, so there's a whole range of things that we did there, and which I'll talk about very, very briefly. Okay, so we did a lot of tests in the lab. We have these equipment, triaxial and simple shear tests. They're fairly sophisticated, computer-controlled equipment to look at the soil behavior, or here the iron ore behavior. Oh, sorry, I pushed the wrong button again. Okay, so just to, you don't need to worry about the shapes of these graphs, but this is the sort of things that you get. So what the point I want to make here is that soil is tricky. Okay, so this is the result of one of those triaxial tests, or it's actually 3 tests, but if we just look at the black line, the resistance goes up to a peak and then drops off, and we're interested in strains here of up to say 5%. And then the dashed line, which goes with that is what's happening with the water pressure. So the water pressure goes up, it goes down, and then it comes back up again. So when we're trying to come up with a model for the behavior, which we need to be able to predict what's going on, what you can hopefully see from this is that the soil response is very tricky. So the model we're going to end up with is, you know, it's not like steel, which is, you've just got a straight line, okay, between stress and strain. Here, this is a highly complex, non-linear stress-strain behavior that we're trying to model. And then we've got cyclic behavior. So these are the results from cyclic tests down at the bottom. The key thing is that we start down here on the right, and then as you cycle it, you move across to the left. And what happens there is the water pressure is going up. As the water pressure goes up, the stability of the cargo goes down. The dashed line represents the failure. So when we come to this line, it fails, although this dark blue one actually failed here when it hit the monotonic curve. Okay, so you don't need to worry about the details. The point I'm trying to make is soil behavior is tricky. It's tricky when it's static. When it's cyclic, it's doubly tricky. Okay, we can skip this. This is just, it's saying what we did. We varied the fines content to look at different materials. Another issue we have, because the soil is frictional, it depends on the stress. So had a PhD student doing this. We basically had a number of parameters to vary, but what we did is we selected one point in the cargo, the red X here at the base. So all our tests started from this same point. Okay, so, but different points in the cargo are going to have different stresses and different changes in stress. So we need to understand the challenges of doing this numerically, experimentally. Okay, so just typical results. We're doing cyclic tests. We're plotting the magnitude of the cyclic loading against the number of cycles. And here these tests are saturated. You can see that it fails very quickly. Okay, we've got 100 cycles. So 0.25 was sort of the maximum value that the shipping companies were talking about, fails in 11 cycles. In a storm, we have maybe 3,000 cycles going for over 8 hours. Okay, so when it's saturated, we have clearly a problem. Then when you do it unsaturated, the curves shift up here. So that means that you get many more cycles before failure occurs. Okay, so this is saying that the TML is good, right? That as we reduce the degree of the saturation of the material, it gets safer and safer. And you can see you don't need to reduce it much to get a very significant increase in the number of cycles to failure. Okay, so centrifuge, I said I'd talk about that. We did some centrifuge tests. Okay, this is what it looks like. It's just a big washing machine. Okay, and looking down on the top, we're putting the soil into these little containers in here. The whole thing then gets spun around. Yeah, so what we did, we spin this up to 1,300 revs per minute, which represents 264 times Earth gravity. And the idea is that when we do that, our 50 millimeter or so height of sample here represents the 15 meters that you have in the ship hull. Okay, so it's a scaling issue. Okay, and then the water comes up, the soil settles, water comes up to the surface, and what we see here, and I know I'm running out of time, is that when you start off with a soil with quite a lot of water in it, so 70% degree of saturation, just from that, the stress, you end up with most of the material becoming saturated. Okay, so although you think you've got, lots of safety because it's unsaturated, in fact, this process of loading the cargo into the ship ends up with a very high degree of saturation, particularly at the base. Okay, we also did column tests where again, you can see the same thing. Now we just shake this and it settles, the water comes up to the surface with the fines. This was an undergraduate project that led to a paper in a major geotechnical journal. Okay, and then we try to model this numerically. So just very briefly, we've got lots of parameters to model the behavior. We've got unsaturated behavior with the water, which also creates extra issues. We then put that into a finite element analysis where we're solving the equations in lots of little bits to try to deal with the nonlinearity. And basically what happens is as you shake it, the effective stress, which starts off like this, reduces down to here because the water pressures build up. So when it gets to here, it's not liquefaction. Liquefaction would be zero effective stress all the way down. But when we get to here, if the ship heals by 10 degrees, then this line here predicts that the soil would not be stable. And the more you go this way, the more the ship can heal without it failing. Okay, so here's the one with 80% degree of saturation. And this one suggests that it will be safe with about 20 degrees heal. Okay, so that's, I'm skipping a lot of the details there because we need to finish. Okay, so we've been trying to work out whether you know, it's safe to ship the cargo. This required us to understand a lot about soil behavior, unsaturated soil with cyclic loading. There's still a lot of work to do. Our results certainly suggest that it's probably okay, but we certainly can't conclude that for now. Okay, so I'm stopping there, but I've been given these questions. So I just need to look at I can't see the chat, so I don't know what people are telling me.
There haven't been any questions in the chat so far.
Oh, okay. That's just you telling me to stop. So.
Oh, yeah, sorry.
Okay, so, I can't see it when we're, you know, in the sharing. Anyway, doesn't matter. So I've got these questions. I'm quite happy to.
I could ask them.
Yeah, go on then.
So, thank you for your presentation.
Yep.
We're going to go on to questions now. So if you have any questions, please pop them into the chat. So the first question I was going to ask you is, you've been in academia for over 30 years. Why have you stayed so long in this field?
Well, it's very hard when you start out to know, you know, what you're doing, right? So, so it's one of your other questions further on down about how did I get here? So I'll answer that and hopefully answer the question you've actually asked in the process, right? So when I was an undergraduate, I came into civil engineering because I was interested in physics. And at the time, physics was only interested in little particles, and they kind of still are, right? And so I wanted to do something practical. So I ended up doing civil engineering. And, you know, I was a student. Structures is easy, right? You all understand that. Everyone does structures. You know what to do. It's straightforward. And I thought that's what I wanted to do. And I went to get a job, and I discovered what structural engineers did, at least what I was told. And I thought, oh no, I definitely do not want to do that. I mean, basically what they said was, you know, so one of the experience, I mean, I had a few, but there was a major power station in the UK. It was about 20 years work for the company that won it. And it was explained to me that the chief engineer who'd already designed one or two of these power stations would basically set it all out. And then all the junior engineers' job was to prove that he was right and do the detail. And I thought, well, what a waste of my time. So I then, you know, had a rethink, right, about where I'm going. And I then went back to the university and said, well, look, you know, this is back to my growing up on the beach. And I said, well, look, I'm really fascinated by how sand moves around on the beach. And, you know, this is a surfing thing, you know, why the breaks change from following storms. And I'd love to be able to do something to do with that. And the professor at Cambridge said, well, that's way too complicated a problem. You know, you can't do that. And I mean, subsequently it's been done, okay, but at the time it was seen as too hard. So then I didn't know what to do, right? And there was a one-year course in soil mechanics. And soil mechanics at Cambridge, I had two professors, Schofield and Roth, that some people will have heard their names. They wrote a very influential book in the 1960s, which really is now taught to all students who do soil mechanics. Okay, so they were big names and they were interesting characters. And so I thought, you know, I'll give that a go. And the more I did, the more interested I became. And I've never stopped being interested. Okay, which is kind of the answer to your question, right? I mean, I'm interested in physics. I'm in understanding what the hell's going on. And as I've gone on, I've realized that people really don't understand what's going on. And, you know, it's been enough to keep me motivated and fascinated. And there's no shortage of problems to look into and play around with. So, yeah, okay, that's...
Yeah, that's great that you found your passion and you stuck at it. I hope everyone can someday find their passion and have a career in it. So another question would be, what do you believe are the most essential qualifications or skills required for someone looking into going to academia?
Yeah, okay. I mean, you know, academia has changed quite a bit over the years, right? So there's a lot more focus on publishing now than there used to be. I mean, it was always important to have a long career, but so it means, you know, you've got to be very well organized, I think, is an issue. And you've got to be interested in really understanding things thoroughly, because without that, you risk, you know, just, you know, you don't have a career, right? You've really got to have something driving you to do it. It can't be enough to just be fascinated by teaching. At the end of the day, if you're not an active researcher, it's pretty hard to have a successful and fruitful career. So you've got to be that, but also, you know, one of the joys is get to work with you guys, right? Is people come in with new ideas and enthusiasm, and you know, there were 3 projects in the work that I just described that were done by students just doing their thesis. You know, so there's plenty of opportunity, and it's not a big jump from where you are to doing research, right? Yeah, anyway, I may be diverging a little bit from the question.
Yeah, that's great to know. So do you have any advice for undergraduates trying to put themselves out there?
Yeah, so that's, you know, so that's a good question, right? So I mean, in soil mechanics, I make a thing about, you know, one of the most important things is communication skills. And, you know, I get you to do things as a result of that. But because this comes from feedback from employers, that the most important thing that stops people progressing, because, you know, people come from Sydney Uni, you know, we know you come in because you're top students, and not everyone progresses well in their career. And a failure to have good communication skills is usually the reason why, you know, smart people don't progress. So it's worth spending a lot of time on just that. It's a skill. It's basically a skill you can learn, but you have to understand that you need to. So another issue is just enthusiasm. You know, if you're an employer, right, you apply, you know, put out a job advert, you get hundreds of people applying. So you've got to stick out from the masses. And this is particularly for your first job. And you know, what they're looking for is, you know, A, a fit with the company, but B, they're looking for people who they think are actually going to stick it out, who really have an interest in what they do. And it's pretty hard to do that if you haven't taken any interest in your undergraduate degree. Okay, and you know, there's a lot of students that don't appear to be all that interested. They're just trying to get through to the other end. You know, my advice is forget work, and I'm dealing with some issues at the moment where people are doing 2 and 3 days work in second year. I mean, my advice is, you know, work out how to live your life that you can be a full-time uni student and really commit to your studies, because you'll never get that opportunity again to really understand thoroughly what you're doing. And, you know, this is, again, feedback that comes from people who've had successful careers and gone on to be, you know, no longer doing technical stuff. But without a solid technical core behind you and a real good understanding, you can't be the project manager. You're just not going to progress in your career. So I think that's the most important thing. I mean, I know it's not a message people like to hear, which is to really focus on your studies. Yeah, anyway.
Yeah, I totally agree with that. We often get told with everyone who's doing PEP, the importance of transferable skills. So yeah. So what was the biggest challenge you faced in your career and how did you overcome it?
Yeah, look, I mean, one answer is I don't think I've ever had a really big challenge. So, yeah, I guess, you know, this is just the nature of the academic job. When I came in, I was very focused on teaching, and I ended up taking a lot of responsibility for teaching within the school and administration stuff and dealing with students, which I enjoy. But ultimately, it doesn't pay the bills. So I had to sort of refocus on the research. And related to that is, you know, in academia, there's and in engineering, there's a lot of focus on maths, but I'm a lab person. You know, you probably know more maths than me, right? So, and so I agonize over that. But over time, I realized that actually I knew stuff that no one else knew. And, you know, so I now see, you know, I feel no threat anymore, but I did feel that I, you know, didn't quite fit somehow for a long time. And, you know, so it's persistence, right? Just persisting at whatever you do, and you will realize after a while that actually you're the expert. And that gives you, you know, the ability to then go on. So, yeah.
There seems to be a question in the chat. So why was the results obtained in the Rio Tinto study still confidential? Would they not benefit from the wider industry as a whole?
Okay, so yeah, look, I'm still in contact with the person that I dealt with in Rio Tinto, and he tells me that, you know, a lot of it now could probably be published, but when you get to deal with companies, they get you to sign all these non-disclosure agreements because they're very concerned about conclusions which, you know, or things that you may say in a report being taken out of context and causing them trouble. So that's kind of the issue. I mean, a lot of the work is in the process. I mean, so we're now 5 or 6 years later. I'm involved actually in 2 papers that are planned. I haven't actually seen anything of them yet, but we have been discussing. So I mean, it will come. It will come. But just more generally, I mean, as I said at the start of the process, all the companies employed academics and other experts to look after their own, you know, self-interest. And what happened was that eventually they reached a point where they all agreed that it was in their combined interest to actually work together and come to the International Maritime Organization with an agreed position. So, you know, common sense eventually prevailed. They all realized that they couldn't actually get a leap on their competitors, and they started working together. So, I mean, it was a very interesting experience to be involved in.
You mentioned earlier some technologies. So where do you think the future of soil mechanics is heading? And are there any new developments or innovations?
Yeah, okay, so that's actually quite a tricky question to answer. So, I mean, you know, my perspective here is I'm the editor of a journal which is focused on supposedly publishing, you know, current new ideas, okay, in geotech. And a lot of the, I guess, the stuff that's new is to do with ground improvement. So looking at ways, so there's an issue with cement. People want to not use cement, it's expensive, it's environmentally not good. So there's people just putting all sorts of things into the ground to try to improve the ground's performance. So there's a lot of that going on. There's also increasingly, just in the last year, probably, a lot of AI stuff. And there's a bit of, you know, these things are fads. Basically, everyone's trying the latest AI thing and then applying it to their problem. So we have a lot of that going on at the moment. Yeah, and unsaturated soil mechanics. This is something that's still very much in the research community. It's just starting to get out into practice, even though unsaturated soil is, you know, basically everything's built on unsaturated soil, and, you know, in Australia in particular, and yet we don't really know how to deal with it. So that's a big area. Yeah, anyway, we could sort of go on, but, you know, there's all sorts of things that are not well understood, that there's minor changes happening.
Yeah, so this will be, I think, the last question. So I've heard you're a keen surfer and sailor. How do you juggle work and other commitments successfully? And do these hobbies translate into soil mechanics?
Well, I think I've answered a bit of your question, right? Is that, I mean, I grew up on the beach, which in England, of course, you don't do very much. You're sheltering behind a windbreak and it's freezing cold. But I'm there in the sand, and you're rebuilding dams and rivers and so on. So I've spent all the time playing the sand, and I still play in the sand. You know, to some extent, I haven't left the beach. But in terms of the work issue, right? So it helps being enthusiastic about what you do and having found your niche in life, because I mean, I put in long hours. You know, most nights I go home, have dinner with the family, and then I'm back doing work for another couple of hours. So I'm working long hours, but it's also important to keep fit and healthy. And so I go running, I go to the gym, I go sailing once or twice a week. You know, and without that, I wouldn't be able to keep doing the other things, right? So it's about finding some sort of balance that works for you. But yeah, I don't know, that's probably what you want to hear. You have to work 10 hours plus a day to succeed as an academic. But anyway,
I think a lot of people would agree in this chat, because we all have a lot of assessments going on right now, and I think it's really important to take that time to do some other things, not just your work. So with that, thank you so much for your presentation. We really appreciate you taking your time out of your busy schedule to do this seminar. I hope everyone watching has gained some knowledge from not only this seminar, but all the seminars in the series. So in order to get those PEP hours, make sure to fill out the feedback form by Friday, the 21st of May. So that's this Friday. And make sure to come to tomorrow's comfort food event, where we will be selling PDAs and brownies. Also today at 5 p.m, early bird tickets for the end of SEM party are being sold for $15. Lastly, thank you everyone for watching, and good luck with exams and assessments.
Okay, thank you from me for everyone watching too. I was surprised by such a big audience. So yeah.
Yeah, a lot of people
thank you.
turn up.
Yeah, and please, I mean, if you have questions, just feel free to email me. I'm happy to try to answer them best I can.
There'll also be a YouTube recording of this up on YouTube, SUCE YouTube. So if you want, you can check that out.